something left Earth on August 30, not a crew, not a probe heading to Mars, something else. Something that got about 48 hours of news coverage and then disappeared from the conversation almost immediately, which is strange because what it is actually doing, what it is actually positioned to find, is the kind of thing that should probably be talked about more than it is. The name is the Nancy Grace Roman Space Telescope. And the way it gets described in press releases and science articles is careful, measured. Words like wide field survey, words like technology demonstration, words like flagship astrophysics mission, all of which are accurate. None of which are the real sentence. The real sentence is this. For the first time in the history of human spaceflight, after Hubble, after Chandra, after Spitzer, after James Webb, after every telescope that got called a revolution when it launched, NASA has finally started building the chain of instruments that leads, directly and deliberately, toward answering whether life exists anywhere other than here. Roman is the first link in that chain. Not the last, not the answer. The first link. And that distinction, that specific gap between what Roman is and what comes after it, is the part that nobody is explaining properly. Start with the number, because the number is where it becomes real. In roughly 30 years of searching, from the early 1990s until right now, every telescope ever built, every mission ever run, every ground-based observatory on every mountain that is ever pointed at the sky has collectively confirmed approximately 6,000 planets beyond our solar system. 6,000, 3 decades. Every instrument humanity had, Roman is expected to find 100,000 in 5 years. One mission, one telescope. 5 years, 100,000 worlds. And when NASA Administrator Jared Isaacman stood in front of the completed telescope at Goddard Space Flight Center in April of 2026, this enormous machine, 42 feet tall, 14 feet wide, sitting in the largest clean room at the facility, he said something that landed and then somehow didn't stick in the public conversation the way it should have. He said what would take Hubble 2,000 years to process, Roman can do in a year. 2,000 years. Sit with that for a second. Hubble has been in orbit for 35 years. It is still considered one of the greatest scientific instruments ever built. And a single Roman observing year renders the entirety of Hubble's remaining useful life into a rounding error. That's the scale of what left Earth on August 30. But the 100,000 planets, the Hubble comparison, that's still not the part nobody is talking about. The telescope is named after a person. And understanding who that person was matters, not as biographical decoration, not as the kind of inspiring background detail that gets inserted into science stories and then forgotten, but because the whole arc of what this machine is and what it's trying to do is inseparable from the arc of her life. Nancy Grace Roman was born in Nashville, Tennessee in 1925. Her family moved constantly, 7 cities before she was a teenager. At some point, somewhere around age 10, they were living on the edge of a small Nevada town. Empty lots on 3 sides of the house, a ranch on the 4th. Dark sky in every direction, the kind of dark that doesn't exist in most places anymore. Her mother, a music teacher named Georgia, used to take her outside on clear nights to look at constellations. Roman said, decades later, that she couldn't really pinpoint exactly when she decided to be an astronomer. But she also said she wouldn't be surprised if those nights had something to do with it. She got her PhD from the University of Chicago in 1949, one of the only women in her cohort. Then ran directly into the wall that stopped almost every woman who tried to do this in that era. Not because she wasn't qualified, she was obviously qualified, but because tenured academic positions were simply not available to women in the way they were available to men. So she moved to radio astronomy at the Naval Research Laboratory and kept going. 1959. NASA is 6 months old. Someone there asks Roman if she knows anyone who might want to build a space-based astronomy program from scratch. She volunteers herself. They hire her, but because her previous work had been so chronically underpaid that it wasn't recognized as formal employment, she gets brought in at the salary level of a new PhD graduate. Despite her international reputation, despite years of research, she takes the job anyway. By 1961, she is NASA's first chief of astronomy. first woman to hold an executive position at the agency. And she reportedly still could not get past the secretaries without stopping to explain who she was, unless she used the prefix doctor before her name, because otherwise they assumed she was there to see the scientist, not that she was the scientist. She used the prefix every time and kept working. The project she poured the most of herself into, the thing that consumed years of sustained effort, was convincing first NASA, then the United States Congress, that a space-based optical telescope was worth funding. This was not a quick sell. She had to build the scientific case from scratch, organize committees of astronomers and engineers, present to skeptical administrators who had other priorities, wait, and present again. She started this work in the mid-1960s. Congress finally funded it in 1977. The telescope launched in 1990. That telescope was Hubble. Hubble's chief scientist, Ed Weiler, called her the mother of Hubble. That became the title that followed her everywhere. She retired from NASA in 1979, but stayed involved as a consultant for years afterward, watching the machine she'd fought for change, the entire field she built. Then in 2018, at 93 years old, Nancy Grace Roman died. The telescope that now carries her name had not been named after her yet. She never knew it was coming. She never saw August 30. Here is the thing that took a while to actually register when going through all of this. Hubble launched in 1990. Chandra came after. Spitzer. James Webb. Each one genuinely changed what humanity could see. James Webb's first images, galaxies from the early universe, rendered in detail that shouldn't be possible, colors that aren't real colors, but represent wavelengths of light the human eye can't detect. Those images did something to people. They still do. But not one of those telescopes was built, from the beginning, to answer the specific question, are we alone? Not as a side project. Not as a secondary scientific objective. As the primary mission, the thing the instrument was designed around from the first proposal. None of them. Hubble was built to see the universe clearly. Webb was built to see the early universe and exoplanet atmospheres. Neither of them was pointed, with purpose and intent, at the question of whether life exists elsewhere. Roman is the first telescope in NASA's history that is openly, explicitly described as a step toward answering it. And even then, even now, Roman itself is not the answer machine. That is the layer that drops out of almost every piece of public coverage. Roman carries two instruments. The wide field instrument is the primary one, a 300-megapixel camera that will spend most of the mission's time doing the planet census, the dark matter mapping, the galaxy surveys. That's the instrument behind the 100,000 planet projection. The second instrument is the coronagraph. A coronagraph does one specific thing. It blocks the light of a star completely, precisely, so that the far dimmer objects orbiting that star can be seen directly. The problem with finding planets through direct imaging has always been the same problem. Stars are catastrophically brighter than the planets around them. Trying to photograph a planet next to its star is something like trying to photograph a single candle flame when it's sitting next to the sun. The star's light doesn't just outshine the planet. It drowns it entirely, fills the detector, makes the planet invisible. Roman's coronagraph suppresses that starlight to a degree that has never been achieved in space before. It can detect a planet 1 billion times dimmer than its star. 1 billion. That coronagraph is somewhere between 100 and 1,000 times more capable than any coronagraph ever previously flown in orbit. And yet, and this is the sentence that changes everything, NASA officially describes it as a technology demonstration. Not the instrument that will find life, not even the instrument that will definitively characterize atmospheres of Earth-like planets. A demonstration. A proof that this level of performance is achievable outside of a laboratory in the actual conditions of space, so that the telescope that comes after Roman can be built with the confidence that the underlying technology works. That telescope is called the Habitable Worlds Observatory. Vanessa Bailey is the instrument technologist for Roman's coronagraph at NASA's Jet Propulsion Laboratory. She described the whole situation in a single sentence that cuts through everything else. She said the performance gap between today's telescopes and the Habitable Worlds Observatory is too large to bridge all at once. Roman's coronagraph is the intermediate stepping stone. The Habitable Worlds Observatory. That name is not an accident. It is not a working title or a placeholder. It is a statement of purpose so direct it almost feels uncomfortable, like someone finally decided to stop being polite about what the goal actually is. The Habitable Worlds Observatory will be the first space telescope in history built specifically, from the ground up, with the singular objective of searching for signs of life beyond Earth. Not as one goal among many. That is the mission, period. It will target approximately 25 Earth-like planets in the habitable zones of nearby stars. Look at them directly. Analyze their atmospheres for the chemical signatures that only biology produces. Oxygen in concentrations that can't be explained by geology alone, methane present alongside oxygen in ratios that don't make chemical sense without something alive to keep producing both, the specific fingerprints of living systems. Now, the Habitable Worlds Observatory does not have an approved budget. It does not have a confirmed launch date. It is in planning stages. The cost and timeline have not been determined. Given the funding environment, the Trump administration attempted to cut Roman's own budget twice before the mission survived those attempts. There is genuine uncertainty about whether HWO gets built at all, or when, which makes Roman's role even more specific. Roman is not just a science mission, it is the argument for HWO. It is the demonstration that proves the coronagraph technology works in space, so that when the time comes to make the case for funding the actual alien life telescope, the answer to, does the instrument work, is not theoretical. It is already answered. Roman is buying HWO the right to exist, and Roman launched 8 months ahead of schedule. Under budget, at a moment when NASA flagship missions almost never come in ahead of schedule or under budget. Someone was pushing hard to make this happen fast. The coronagraph is the part of Roman that connects most directly to the alien life question. But the wide-field instrument is doing something that operates at a different kind of scale, one that quietly reframes what habitable even means. The 100,000 planet projection comes primarily from transits, watching enormous numbers of stars simultaneously for the tiny, brief dip in brightness that happens when a planet crosses in front of them. Roman catches these by sheer volume, covering a patch of sky 100 times larger than Hubble while maintaining the same image sharpness. But the other detection method Roman uses is gravitational microlensing. And this is where something genuinely unexpected comes in. Microlensing works through alignment. Two stars happen to line up, one far in the background, one closer to Earth. The gravity of the closer star bends and briefly amplifies the light coming from the distant one. If a planet is orbiting the foreground star, it creates a secondary distortion in that amplification, a specific signal in the light curve that reveals the planet's mass. The critical thing about microlensing is where it finds planets, not close-in hot worlds near their stars. It is uniquely sensitive to planets in the cold outer regions of solar systems. And, more importantly, planets that aren't orbiting any star at all, rogue planets. Worlds that were ejected from their home systems at some point in their history through gravitational interactions with other planets or passing stars, and now drift completely alone through interstellar space. No star, no orbit, no light. Just a planet, moving through the galaxy in permanent darkness. Before Roman, the estimate for how many rogue planets it might find was around 50. Then, Naoki Koshimoto, a researcher who had been at NASA Goddard and moved to Osaka University, reanalyzed the existing microlensing data with updated simulations of Roman's capabilities. His new estimate was 400 Earth-mass rogue planets, just within Roman's primary survey zone, 8 times the previous estimate, because it turns out rogue planets are far more common than anyone had assumed. 400 worlds, untethered, dark, drifting alone in the space between stars. And here is the part that is technically speculative but physically not impossible. Some rogue planets, particularly those with rocky cores and enough mass, retain internal heat. Radioactive decay in the core generates warmth that has nothing to do with a nearby star. Some may have enough of that internal heat, combined with the right atmospheric pressure, to maintain liquid water somewhere beneath an icy surface. Life, at least life as understood here, does not actually require a star. It requires energy and liquid water. Some rogue planets might have both, drifting alone in the dark, completely invisible to every telescope ever built before Roman. Roman wasn't even primarily designed to find those. They are almost a side effect of pointing the telescope at the galactic center for long enough. There is one detail about Roman that almost never makes it into mainstream coverage. The primary mirror, the 2.4-meter optical element at the heart of the entire telescope, the thing that collects the light from 100,000 planets, was not built by NASA. It was built by the National Reconnaissance Office. The NRO is the U.S. government agency that builds classified reconnaissance satellites. Spy satellites. The ones that photograph things from orbit that other governments don't want photographed. At some point, this mirror became surplus, no longer needed for whatever it was originally built to do. The NRO donated it to NASA. NASA accepted it, modified the surrounding systems to turn it into a science instrument, and that mirror is now at the center of Roman. Nobody has said publicly what the mirror was originally built to look at. That information is classified. So the optical element that is currently moving through space toward the Sun-Earth Lagrange point, the mirror that will spend 5 years mapping alien worlds and proving the technology that leads to the first alien life search telescope, that mirror started its existence as part of a program whose purpose is still secret. It spent its early life looking down. At Earth. At people. Now it is pointed at the stars. That doesn't have a clean meaning. It's not a metaphor for anything obvious. It's just the actual history of the object, and it sits there without resolving into something comfortable, which is maybe why it rarely gets mentioned. Romans spent 60 years building instruments to see the universe more clearly, not for a single grand goal, just the next instrument, the broader view, the cleaner data. The orbiting astronomical observatory in the 1960s, Hubble through the 70s and 80s, always pushing for what came after the current thing. She said near the end of her life that she was glad she ignored everyone who told her she couldn't be an astronomer. Said it without bitterness, like it was just a fact about decisions she'd made a long time ago. She died in 2018 without knowing a telescope would be named after her, without seeing the funding fights, the assembly at Goddard, the move to Kennedy Space Center in June of 2026, the launch on August 30, without seeing any of it. And there is something in that which doesn't resolve cleanly either. Because she never set out to build the alien life detection chain. She set out to build the next instrument. And then the next one after that. And what that chain of instruments has become, 60 years later, with Roman now in orbit and the Habitable Worlds Observatory waiting to be funded and built, is humanity's first serious, deliberate, purpose-built attempt to find out whether anything else is alive in the universe. She built it without knowing that's what she was building. The telescope named after her left Earth on August 30, 2026. Her institutional fingerprints are in the design philosophy, in the technical lineage, in the argument that space-based observatories are worth fighting for. She is inside the structure of the thing in a way that is not metaphorical. And that machine is now sitting in space, 1.5 million kilometers from Earth, carrying a coronagraph that is the prototype for the instrument that will one day look at a planet in the habitable zone of a nearby star and check whether something is alive there. The Habitable Worlds Observatory may or may not get funded. The timeline is genuinely uncertain. The answer to the question, if an answer comes, might be decades away. But the chain started. That is what August 30 was. The beginning of the actual attempt. Not a new telescope with a bigger mirror. Not another revolution in how clearly humanity can see distant galaxies. The beginning of the attempt to find out whether anything else is out there, conducted with purpose and intent, using instruments designed from the start for exactly that purpose. Something left Earth on August 30. Now you know what it's actually looking for. And now the question that sits underneath all of it, the one that doesn't go away, is whether we will still be here and still paying attention when the machine that finds the answer is finally ready to fly. Nancy Roman never got to find out. That part is just true. What do you think we'll find when the real search begins? Drop it below.